All right, so a quick summary of when we're looking at transport in animals and plants. One of the first things we have to appreciate is this idea of something called surface area to volume ratio and the impacts that it can have. So there's an image of four very different organisms here. We've got bacteria, fish, mammals, and an insect. And they've all got one thing in common. They all need oxygen and they all need nutrients. And how they get it is very different. So we'll come back to a second. If you look here, you can see there's a box here which has got, it's 1 centimetre by 1 by 1. Okay, so if it's got 6 sides, it has a surface area of 6 centimetres squared. Its volume, you'd have to do width times depth times height would be 1 times 1, gives you a volume of 1. So overall, its surface area to volume ratio is 6, because to work out surface area to volume ratio, we have to do, if I just write it here, there we go. Ratio equals surface area divided by volume. So we do 6 divided by 1 gives us 6. And this one here is, as the object gets bigger, well, you can see its surface area has got bigger. It's 24 now. But its volume has also increased to 8. So now if we do 24 divided by 8, we only get a surface area to volume ratio of 3. And then again, as the object gets even bigger, of 4 by 4 times 6 sides, 4 times 4 times 6 gives us a total surface area of this cube as being 96 centimetres squared. But its volume is also getting much bigger, of 64. So now it's only got a surface area to volume ratio of 1.5. So what's strange is, as objects are getting bigger, the ratio is getting smaller. And this is applying to these organisms here as well. Although a bacteria has a very, very small surface area, in comparison to a polar bear, its ratio is much, much bigger. So what impact might that be having on the polar bear? Well, if you think about this bacteria, it is getting its oxygen just by simple diffusion. So let's make it a different colour so we can see it. So oxygen can just diffuse in quite easily. Okay, from all sides. And it's got such a small volume that actually its metabolic demands are very low. So just this simple diffusion is enough to sustain its needs. But this insect now, it's still very small, but in comparison to a bacteria, it's millions of times bigger. So although it is getting its oxygen through its surface, it's got little spiracles behind its legs just here. Little spiracle just there. There's a little hole where the oxygen can enter. But this locus can't just rely on simple diffusion, because its volume is already much bigger, and therefore its surface area to volume ratio compared to the bacteria is much smaller. So it's having to, there's adaptations to try and bring the gases in to the center of this locus, where it can get oxygen to as many cells as possible. If the cells in the center were to rely on oxygen that diffused all the way through, then by the time the oxygen got there, it would have been used up anyway. So there has to be a way to try and get the oxygen into every cell in the body. So we look at these cubes. As they get bigger and bigger and bigger, the surface area to volume ratio gets smaller. And you can imagine if this cube needed oxygen to stay alive. Imagine what the very centre cube in the very middle of this big cube, what the impacts are. It's going to be very difficult for the cube right in the middle to get any oxygen because it has to get through so many already. So how can we get oxygen to those? Well, if you look at just this basic square here, you can see it's got a surface area that it's represented by this side here, this side, and this side. And a simple adaptation we can do now to increase the surface area is to cause this little extra cleavage here, where it could just come in. And already that's beginning to increase the surface area of this square. Or the shape could change again. We could get it to come in and have this other little intrusion here. And that again is causing the surface area to increase as well. And here again, it's getting more advanced. All these little wiggles are causing the surface area to increase again. So if you think about it, this image you're seeing here is looking a bit more like the lungs. The lungs are almost like the external part of our body, like our skin, but it's going inside our body. So it's the inner boundary that separates us from the outside world. Because when you breathe in, you are bringing the outside world, the air, into this area here. And if we can get this area to have as many intricate shapes that help to increase surface area, that's going to mean more and more diffusion and more gas exchange taking place. So what do these features look like? Well, let's have a look at what the different ones are doing. So you can see here now, hopefully, look at it's almost like a cauliflower. There's so much little intricate shapes to this as it branches from the trachea to the bronchi to the bronchioles and down to the individual millions and millions of alveoli. So this is something you would have gone through in GCSE. This structure is increasing our body's gas exchange surface to be the equivalent to a tennis court. So rather than just, if we go back to this polar bear, rather than just relying on oxygen maybe diffusing into its skin, like maybe the bacteria has, that wouldn't be very effective. Now there's a big set of lungs within here which will make the equivalent of a surface that's much bigger than this polar bear's skin. Here's the locus I talked about. The little spiracles are found. You can just see it on the edges, these little black dots, which I'm colouring red. They're helping to bring air into the centre where there's a greater surface area, so that more gas exchange can occur more effectively. And the fish as well. Well, they don't breathe, but there is a form of ventilation happening. Every time they open their mouth is filling up with water, and when they close their mouth, they force water out to the side of their head. Imagine having slits on the side of your jaws where you could drink. Imagine you could take a glass of water into your mouth, close it, and then you could squirt water out the back of your jaw. That's what fish are doing. And if you look here, there's another really intricate adaptation called the gills. Again, the purpose being to increase the surface area by a great amount. So all of these features, lungs, tracheoles, and gills, these are all adaptations that have occurred in response to the fact that as we get bigger, our surface area to volume ratio decreases.